everyone. In this video, I'm going to go over the Friedel acylation reaction. And essentially what we're going to be doing is we're going to be taking toluene and what is called acetyl chloride. You'll notice this looks a lot like acetic acid with an OH. If it was acetic acid, it would have an OH here, but it has a chloride here. We call this acetyl chloride. We're going to use a catalyst, aluminum chloride, which has safety implications because this will react fairly violently with water and produce HCl gas. So you got to be careful with this. Not only is it dangerous if it produces HCl gas, it also ruins the catalyst and it won't work. So you got to make sure that you keep this dry. We're going to try in this reaction to produce 4-methylacetophenone, this molecule here, and HCl is a byproduct. So I want to talk a little bit here about how the reaction is going to go. Then we're going to look at the mechanism of the reaction. Then I'm going to talk a little bit about the theoretical yield. I will discuss, but not go over, the separation scheme, and then we'll talk about the how we're going to analyze our product by IR, and finally we'll talk a little bit about the hypothesis. So let's get started. First of all, we're going to do this reaction in a specific way, and it's important that you're familiar with the specific way, so I'm trying to get this all on the screen at once, so that we can discuss what's basically going to go on here. So first thing is that we're going to do is we're going to put into our 3-neck flask. So we have a 3-neck flask here, we have a separatory funnel here, we have a drying tube here. Remember I said water is bad, it'll destroy our catalyst. We have a condenser, we have our gas trap here, and we can trap the HCl, which is a product of this reaction, using the gas trap. So this isn't exactly what you're going to use is going to look like, okay, but it's somewhat similar to what you're going to look like. So this is that. Notice that you have an ice bath and a stir plate, and your gas trap will look a little bit different, but it's the same idea. So what we're going to do is we're going to put our aluminum chloride in dichloromethane here. Specifically, we're going to put 7 grams of aluminum chloride and 12.5 milliliters of dichloromethane into our round bottom flask. And we're going to stir that up. Okay. Then what we're going to do in the hood is put our acetyl chloride and in dichloromethane, specifically 4 grams of acetyl chloride and 7.5 milliliters of dichloromethane in the separatory funnel. Then we're going to open the separatory funnel a little bit so that over 10 minutes, okay, this is only going to have a total volume of somewhere around 10 or 11 milliliters, and over 10 minutes you're going to slowly add that acetyl chloride into the aluminum chloride that's in this flask. So acetyl chloride in dichloromethane here, aluminum chloride in dichloromethane here. We slowly add over 10 minutes. This will allow us to form what is called the acylium ion. And I'll talk about the mechanism of that in a few minutes. So this will form the acylium ion. Once we've formed the acylium ion, we're then going to put toluene in dichloromethane here. Specifically, we're going to put 0.0375 moles of toluene and 5 milliliters of dichloromethane. Then, drop-wise, over about 10 minutes, we're going to add that into here. So there's 2 reactions going on here. First, we have the acetyl chloride in dichloromethane here interacting with the aluminum chloride to form what's called the acylium ion. Then the acylium ion, second, will react with the toluene in dichloromethane here, and we'll add that second. So first 10 minutes, acetyl chloride in dichloromethane, second 10 minutes, toluene and dichloromethane. And you have to do it in that order, because if you don't have the acylium ion, it's not going to react with the toluene. So we got to form that first, then react with the toluene. Note that we're doing all of this using a gas trap because one of the products of the reaction is HCl. One last time. We're going to add this in dichloromethane to the separatory funnel. We're going to add this in dichloromethane to the flask. We're going to add this over 10 minutes to the flask. Then we're going to put this in dichloromethane, this is toluene, and then we're going to add that to the flask over 10 minutes after we've added this one over 10 minutes. So I hope that's clear. I know I said it several times. All right, so now that we have an idea of specifically how we're going to do the reaction, let's look a little bit about the mechanism of the reaction so that we have some idea of why we're doing it in this order and what's going on here. So in the first part of the reaction, we're going to mix the acetyl chloride in the separatory funnel with the aluminum chloride in the flask. And note that they're both dissolved in dichloromethane. So aluminum here has an empty orbital. So this empty orbital is capable of accepting electron density. Well, what has electron density? Chlorine has electron density, so we have this going in here. So in this case, the chlorine is acting as a nucleophile going towards the aluminum, which is acting as an electrophile. So remember that when you're writing up your mechanisms, you should identify the nucleophile and the electrophile in each step. I'm not going to do that for every single step, but I would like you to do that, because then you have to think about it for each step. So what we have here is we have CH3 bonded to C, double bond O, bond Cl, like this. And we have this bonded to the aluminum, which is bonded to 3 more Cl's like this. And now the aluminum has extra electrons around it, and the chloride has less electrons around it, the chlorine, so the chlorine is plus and the aluminum is minus, because we added electron density to aluminum, and we essentially took electron density away by sharing from chlorine. So then what happens? This bond here is going to break. And what we end up with here is we end up with CH3 bond C, double bond O, with a plus charge on the carbon, and we end up with Al, Cl, 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 Cl. So aluminum with 4 chlorines on it, like this. This aluminum here is going to have an extra electron around it, so it's negatively charged. And essentially, this aluminum is going to want to get rid of a proton, which it can't do. There's no source of proton yet, theoretically, until we add the toluene in. But basically what's going to happen is, if there's a proton around, this Cl is going to go with the proton to form the HCl gas that we're going to form, and this will go back to being neutral. Said another way, it's a catalyst because it's reformed. However, what is important here is that we have formed what is called the acylium ion. And the acylium ion, this positively charged species here, is a very good electrophile. So when we form this acylium ion in solution, we can then secondarily react it with the toluene by putting the toluene in the separatory funnel in dichloromethane and adding it over 10 minutes. So the next thing in the mechanism that I want to talk about is the interaction of the acylium ion with toluene. So let's look here. I'm going to move the paper. We have CH3C double bond O with a plus charge here. And you could theoretically write a minor contributing resonance form where the plus is here and you have a triple bond. So essentially these electrons come down and you have a plus here. So it is somewhat resonance stabilized, but it's a very good electrophile. So let's look at what we've got. Well, what are we going to add into the solution? What we're going to add into the solution is toluene, which is methylbenzene here. What's going to happen? Well, it has basically 3 choices to attack: the ortho, the meta, and the para. And, the ortho, the meta, and the para. So I think I said that wrong. So the ortho, the meta, and the para. So this one has a methyl group attached to it. So this methyl group is capable of donating electron density. The reason that it's not going to favor the ortho position is because the methyl group is present, and there is some steric hindrance, so it's harder to get to the methyl position. So what I want to look at is the attack of this acylium ion on the para position. So essentially what happens is these the attack by the para position onto this. So these electrons come here. Okay, this is an electrophile. The double bond here, the pi bond, is the nucleophile, and what we end up with is this molecule. We end up with, here, we now have a new bond. I didn't give myself enough space to write it in the brackets. All right, here. We have a bond here. We have a bond here, because they're just going along for the ride. And we have the methyl group here going along for the ride. And we have a plus charge here. Well, let's look at the resonance forms of this. This molecule, or this double bond, can flip over. And we end up with a resonance form here, where we have the ring. The double bond now moves from here to here. This double bond goes along for the ride. This goes along for the ride. And this goes along for the ride. But the plus charge is now moved. The plus charge is here. The plus charge, being adjacent to an electron donating group, although weakly electron donating, it is an electron donating in an activating group. This stabilizes this positive charge because this methyl group can donate electron density for the exact same reason that a tertiary carbocation is more stable than a primary carbocation because of something called hyperconjugation. So this molecule is, this methyl group is able to donate electron density. Let's look at the other resonance form. And what we find is now this double bond moves, so it's here. This double bond stays, the methyl group stays, the C double bond O, bond CH3 stays. I apologize because I'm not writing this super clearly. I'll put it over here and I'll put the arrow up here so it's a little more clear. Okay, and now the plus charge is here. And these are the three resonance forms. The reason that this is an activating group and an ortho-para director, you'll get the same resonance forms if you draw the ortho products, is because the positive charge can be adjacent to the electron donating group. That is very important to remember. So when you're looking at why it can't be meta, what you're going to find is if you put it attack at the meta position, either this one or this one, what you're going to find is you can never get this positive charge when you draw the three resonance forms adjacent to the electron donating group. Now this isn't like the organic chemistry lecture class, so I'm not going to go into that in great detail, but in electrophilic aromatic substitution, you will go into that in great detail. Alright, so now what happens? Well, we can pick essentially one of these resonance forms, but something is going to come along and take an H. So what I want to do is pick the original resonance form and explicitly show the hydrogen that's on it. Now I'm going to use my Al, Cl, 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 and how exactly this goes is not super important, but essentially we have this minus charge here, so this would like to get rid of a chloride, and the chloride would like electron density, or like to share that electron density. So basically what's happening is this goes here and grabs this proton, and this electron density goes here. And what you end up with is, let me put it on the screen, the ring. Now you're back to three double bonds. We have the methyl group, we have the C double bond O, bond CH3. So essentially something comes along and takes this proton. These electrons come back to here, which makes this no longer positive because now you have this double bond. Aromaticity is restored, that's the driving force of this step of the reaction, plus HCl, the byproduct, and the reason we have a gas trap, plus we regenerate the catalyst, AlCl3. So this is essentially how this reaction is going, and this is the mechanism of the reaction. I apologize, it's a bit messy. I made a couple of mistakes there. So now that we've talked about the mechanism, let me do an example of the theoretical yield. Note that I'm going to use different numbers like usual so that we don't get the exact same answer. So in the real lab, we're going to use 0.0375 moles of toluene. And I'm going to use that as, in the example, so this is real or actual, and in the example, I'm going to use a little bit less than that, 0.0250 moles. For the acetyl chloride, we're going to use 4 grams in both cases, but it's not the limiting reagent, so it's not going to matter. And AlCl3 is a catalyst, so we don't need to consider that. So I'm going to do the toluene using the example 0.25 moles, 0.025 moles. So 0.0250 moles of toluene. We want to convert that to moles of product, which is 4-methylacetophenone. So I'm going to call it 4-MA, 4-methylacetophenone. And basically it's 1-to-1. So for every 1 mole of toluene, I think I added an extra N in there. For every 1 mole of toluene, we're going to get 1 mole of 4-methylacetophenone. Then we need to convert it to grams of 4-methylacetophenone using the molar mass, which happens to be 134.18. So for every 1 mole of 4-methylacetophenone, it's going to have a mass of 134.18 grams of 4-methylacetophenone. When we do all that math, we get 6.84. Oh, I apologize. That's the wrong one. We get 3.35 grams of 4-methylacetophenone. So this is the yield using 0.025. Note you're going to use 0.0375. So now let's do it for acetyl chloride, which is not the limiting reagent. This is the limiting reagent, so this will end up being the theoretical yield. So if we start with 4 grams of acetyl chloride, I'm going to call it AC just for short, we need to convert that to moles. Well, for every 1 mole of acetyl chloride, it has a mass of 78.49 grams of acetyl chloride. Now we want to convert it to 4-methylacetophenone. It's still 1-to-1. So for every 1 mole of acetyl chloride, because there's a 1 out here, we get 1 mole of 4-methylacetophenone. Now we want to convert it to grams. We have the molar mass. So for every 134.18 grams of 4-methylacetophenone, that's 1 mole of 4-methylacetophenone. So same conversion factor. When you do that math, you get 6.84 grams of 4-methylacetophenone. So, in this case, the theoretical yield is 3.35 grams, and the limiting reagent is toluene. In your case, the limiting reagent would be toluene. You'd have to do the math to know that, but I've done it in advance, so I knew that. But you're not going to get this theoretical yield. Now, the other thing that we need to consider here is that how am I going to add 0.025 moles of toluene? That's not a thing I can measure, right? There's no mole measuring device, if you will. So let's convert this to a usable unit. Well, if I have 0.0250 moles of toluene, I first want to convert it to grams. So 1 mole of toluene is 92.14 grams of toluene. Then we want to convert it to volume because toluene happens to be a liquid at room temperature. So there are 0.867 grams of toluene in 1 milliliter of toluene. Said another way, the density of toluene is 0.867 grams per milliliter, but we need grams on the bottom because we want grams to cancel out. So now we can figure out how much toluene we should measure out, which for my example is 2.67 milliliters. But remember, my example was 0.025 moles. You're using 0.0375 moles. So you're going to need to redo this math and redo this math for the appropriate amounts of toluene that you're actually using in the reaction. So now I want to talk briefly about the separation scheme. So during the reaction workup, you're going to add some ice, and then you're going to pour some concentrated HCl on that. It's very important that you add the acid to the ice, or the acid to the water. Ice is made out of water, of course, and not the ice to the acid. So make sure you add the HCl to the ice. And what this purpose of this is you're going to get some aluminum salts, and it'll make sure the aluminum salts stay soluble. It'll also destroy any unreacted aluminum chloride and convert it into essentially acetic acid. So this is basically why we're going to add this. So when you do add this, it's going to change slightly what is in the beginning of your separation scheme. So at the beginning of your separation scheme, hopefully you have some 4-methyl acetophenone, because that's the product you were trying to make. Okay, so there should be some of this here. All right, you're also going to have dichloromethane, because lots of dichloromethane was used as a solvent in all the steps, so that's still going to be there. Okay, you're going to have HCl, both because it's a product of the reaction and because you add a whole bunch of HCl. So you're going to have 25 grams of ice. You're going to add to that 12.5 milliliters of concentrated HCl, as I said before, to work it up and keep the aluminum salts soluble. Any unreacted acetyl chloride is going to become acetic acid. And the aluminum, who knows what it is, okay? Maybe it's aluminum chloride, maybe there's some hydroxide there, although there shouldn't be too much in a strong acid. I'm just going to call it aluminum salts. So there's going to be some kind of aluminum salts in this system that we can get rid of. So this is essentially going to be the top of your separation scheme. Now, as promised, I'm not going to go over the whole, that should have an L, I'm not going to go over the whole separation scheme, but I did want to give you an idea of where to start. So you're going to start here, then think about how you're going to extract it, what traces of things are going to be left, how are you going to remove those traces of things, okay, so on and so forth. I guess we could put at the top of this also water, because we added a bunch of water, so it's probably not a bad idea. All right, so this is basically the beginning of your separation scheme, and you're going to do liquid-liquid extractions, you're going to get rid of acids using bases, you're going to use drying agents, and then you're going to evaporate the solvent. That's essentially what the plan here is. So one of the things you're going to do after the end of the reaction is you're going to do IR on the product. And I wanted to look at the difference between the IR of toluene, the starting material, and the 4-methyl acetophenone, the product. So here I have the IR of toluene. You'll notice that it has CH, aromatic, and CH, aliphatic, if you will. So the methyl group gives you the CHs below 3,000, and the ring gives you the CHs above 3,000. So these are essentially the two peaks that we can identify. How does that differ from 4-methyl acetophenone? Well, in 4-methyl acetophenone, we still have the aromatic CHs, we still have the non-aromatic CHs, so we have CH aromatic above 3,000 and CH aliphatic below. But what do we have now? We have this carbonyl peak. And this carbonyl peak, somewhere around 1700, this C double bond O, is a major difference. Toluene, if we look here, has no major peak around 1700, very strong peak. But if we look at the 4-methyl acetophenone, we get a peak all the way down to the baseline at around 1700 because this is the C double bond O peak. And that makes sense, right? Toluene doesn't have a carbonyl group, but 4-methyl acetophenone does. Just for comparison, because it is going to be part of the reaction mixture, this is the IR spectrum of dichloromethane, and there are 2 hydrogens here, so you can see those CHs here. But of course, there's no aromatic CHs in dichloromethane. It's not a bad idea sometimes to get an idea of what the solvent's going to look like, because maybe it didn't all come out, or maybe some of it distilled over, or whatever. So it's not a bad idea to have an idea of that. So the last thing I wanted to talk about very briefly is the hypothesis. It says focus on the reaction and which position the electrophile will attack. Include formation, yield, and characterization of the product. So focus on the reaction. We talked about the reaction. We formed the acylium ion by adding the aluminum chloride, and that then acts as an electrophile for nucleophilic or electrophilic aromatic substitution, and it's going to mostly attack at the para position. Why the para position? Because the plus charge can be on the methyl group, or said more generally, a methyl group is an activating group, and a methyl group is going to stabilize that positive charge. Why not the ortho position? Because this is also true of the ortho position. Well, there's some steric hindrance at the ortho position because we have that methyl group on there, so that may limit the amount of ortho product. Why not the meta position? The meta position won't be coming at all because in the meta attack, you can't put that positive charge on the adjacent position. And I leave it to you to draw those resonance forms and prove that. I don't want to do all of it for you, so therefore I strongly suggest attack at the meta position, okay, 2 carbons away from the methyl group, and see where the positive charge goes in the 3 resonance forms. What you should find is it'll never be adjacent to that methyl group, so therefore the resonance stabilization and the stabilization from that electron donation doesn't happen. So now we want to include formation, yield, and characterization of the product. So we've talked a lot about the formation. So the yield, okay, we talked about how to calculate the yield, and so therefore just change those numbers. And then characterization of the product, we talked about the IR spectrum here as far as characterization. The melting point of the 4-methylacetophenone is very close to room temperature, so you're not going to be able to report the melting point. But you do want to make sure you weigh the bottle before you do it, so that before you distill off the dichloromethane, so you can calculate the yield of your product by mass. So you can subtract out the weight of the flask essentially. So that's basically it. I hope that you found the video helpful, and thanks for watching.